Well, I'm recently retired. I've lived in Madison for the last 40 years. Basically, I took over John Curtis's job. People said, well, why did you come here? I said, for the best ecology job in the world. And I was trained in North Wales with a group of people who really very much admired John Curtis's work here in Madison. Curtis developed ways of looking at vegetation to the extent that Wisconsin's the best described vegetation in the world, at least up until 1990, and is still better described than almost everywhere else. And the techniques he used was to jury-rig together multivariate analysis. So I'm sort of a multivariate statistician, but informally trained. I'm an ecologist, and the effect of looking at large-scale things like plant communities is it tended to move me upscale. So I got interested in issues of scale, and then started to realize some interesting difficulties there. A sort of Hegelian switch from quantity to quality. As you move upscale, sometimes you just get more, but sometimes you get different. And a body of theory that I pretty much established in ecology is called hierarchy theory. Engineers don't particularly use it, although they use scale a lot, because they're fully competent at getting their numbers right. What they're not particularly interested in is when suddenly there's a qualitative change because you got bigger. In fact, when there's a qualitative change because you got bigger, what they build falls down. They're very competent at doing that, but they're not particularly interested in meaning and shift of meaning and role of the observer in the system, which is essentially where I've come from. So I've got into looking at things at different scale and finding out essentially what is the role of the observer in observing complex systems. Robert Rosen, who's probably the smartest guy I met, and I was so privileged when his daughter Judith came to my retirement party, which was just recently. Robert Rosen identifies that a system is complex if you can't model it, which has some very interesting consequences, because if you can't model it, you either can or you can't. So it's either complex or it's not. So what do you do about systems that are more complex? Degrees don't count, and yet most people think about complexity in terms of degrees of complexity. So essentially, what hierarchy theory does is to take systems which are nastily undefined and defines them according to appropriate levels, and basically at that point makes them simple enough so that you can model them. But of course, once you can model them, the complexities disappear. The reason why you study complexity is to get rid of it, so that you can indeed model it. So there's some interesting issues here. So most of the discussions on complexity are not about complexity. They're about what you had to do to make it simple enough so you could model it. And then the more you had to do, the notion is, the more complex it is. But I take that pretty hard line about systems which are not only undefined, but undefinable. At that point, big boy, what do you do? Because science depends upon things being defined. Now, issues of sustainability are hot. Lots of people are excited about that. And about 15 or 20 years ago, the notion of livability turned up. And there's a lot of hand-waving about that. I've done mine, and I'm here to tell you what I think about this. My view is not particularly optimistic, but what it does say is when the system is corrupt and necessarily broken, what do you do anyway? Because somebody's got to handle those situations where normal, mechanistic, reductionist science breaks down. In the end, we use models, but we use models to generate narratives. Narratives are the end product of science, not models, narratives. You use your models to improve the quality of your narratives. The great thing about models is they're internally consistent. The bad thing about models is they have to be internally consistent. So what the hell do you do with one man's terrorist as another man's freedom fighter, because X has two different meanings at that point? You obviously have to have a discussion. There are various strategies. You could develop models of that, but it would be things like, he's a Palestinian bastard and he had it coming. You know, at that point, but that's not going to get you very far. I mean, or alternatively, he's an Israeli bastard and he had it coming. So, you can't do very well there. You could remove all values from it and just talk about shock waves of 3,500 miles an hour tearing buses apart, but that's not going to solve your problems either. The obvious issues with Palestinian-Israel problem is you've got to fit those inconsistencies together. You have to be able to hold two sets of values simultaneously. And the great thing about narratives is they let you do that. The wonderful thing about narratives is they're not true or otherwise. They're not true or not true. Truth is not the issue. In science, I think we have to do our best to develop narratives that we would have every reason to presume appropriately represents the situation. In other words, just sort of going into a deep postmodern point of view and saying it's all what we think anyway, so I can pull any crazy idea I want out of my ear. The answer is, well, yeah, you could, but it ain't going to get you anyway. So what do you do in a situation where things are not just undefined, they're undefinable? And sustainability is exactly that. Sustainability is one of those really nasty things which is undefinable. So I have strategies for dealing with this and building appropriate narratives. Narratives are absolutely crucial in dealing with livability and sustainability. We seem to have a lot of catchphrases in my lab that capture a lot of what we do. One of them is, what's the same when everything's different? And that happens a lot. Situations radically change, but on the other hand, how come you're still talking about them in the same terms? For example, you may be familiar with Studebaker. It used to be, when it was, now we're down to the big 1.5, but when it was the big 4, one of the big 4 was Studebaker. And they made fancy cars in South Bend. And the original Studebakers, though, Ulysses Grant had a Studebaker as his carriage. And in fact, his son gave it to Studebaker in 1910. The critical thing is that Studebaker made its first luxury automobile in 1910 and stopped making carriages in 1915. In other words, everything's different. I mean, nothing's the same, except that they're still in luxury transportation. And so, how do you deal with situations which are completely different, but on the other hand, you're still talking about them, so in some sense, they're the same? How do you deal with moving off into a future with different levels of analysis and different approaches? Another strategy which I have which is very helpful. Is to, and biologists sort of know this, but they don't seem to formalize it. There are two parts to biological and social systems. One of them depends upon thermodynamics and will yield to the equations of thermodynamics. That is to say, I eat breakfast and I decompose it at a rate and extract organization from that. If I got my breakfast, which was a bowl of cereal, and didn't put milk on it, and then for some reason or another I died, or I didn't go home, or what, that bowl of cereal would remain high quality food for months, even years. I mean, maybe the odd mouse will find it, but I mean, in general terms, but if I eat it, it doesn't take many hours before it's completely degraded. So what you have is high quality materials in a world. Biological and social systems take in those high quality materials and they degrade them. They're taking a process that would be a very gradual degradation and degrades them very steeply. And in doing so, they extract order out of that. So biological systems create disorder while in the process of extracting order. So it looks like they deny the second law of thermodynamics. If you find yourself denying the second law of thermodynamics, you're wrong. You're always wrong. You're consistently wrong. And there's nothing to be done about that. On the other hand, there are some interesting wrinkles. I get really pissed off at physicists because they are so goddamn pleased with themselves. And I get really upset with biologists touching the forelock to the physicist. It's all basically physics. No, it's not. Basically, we don't have a physics for biology. Schrödinger pointed that out in 1944. It was true then, and it's still true now. Physicists can't do their bookkeeping unless the system is closed and unless it's close to equilibrium. They can't do their bookkeeping if you don't allow it. The trouble is, biological systems are open and they're not of interest unless they're far from equilibrium. I mean, you could get hold of a rat, stick it in a plastic bag, closed system, right? The rat would die, and indeed the amount of entropy would go up. You'd have a sort of gooey mass of rat. But it's not very interesting. I mean, not unless you're a bacteriologist. But what you need to do is open the bag and introduce him to a lady rat, and all sorts of other stuff happens, right? In other words, there's something going on in biology that cannot be discussed with a closed system at equilibrium. See, closed system and at equilibrium is an assumption. All assumptions are false. That's how science moves forward, by showing in particular how the assumptions we used to rely upon are false. Somehow or another, there's always a bunch of optimists now who think that their assumptions are true. But no, all assumptions are false. So the idea here is not to find out which assumptions are true, because they're all false. What you're trying to do is to work out what assumptions can you make while at the same time still being able to predict. In other words, science is about not finding the truth, but identifying which lies can you get away with. It's completely backwards. And so, as physics tries to work here, even in physical systems, the system isn't closed and it's not at equilibrium. So it's not true for them either, but they get away with it. The trouble in biology is you can't get away with it. The biology is not interesting. So we need then to deal with a biology that's far from equilibrium. So there's a thermodynamic part of biology, and you keep on sticking stuff into the biology, it holds it away from equilibrium, and out of that, wonderful emergent structures occur. James Kay, wonderful scientist. Oh, I was so sad. He didn't even make it to 50. That was not fair, because he was a good, kind, generous, and a wonderful Canadian scientist. And he, along with Schneider, Eric Schneider's still around,